Hi, I'm Tom Costello. I'm a signal processing engineer at Astronics Test Systems. And this is our ATS 3100 radio test set. It's a software-defined instrumentation platform for RF test. It hosts a suite of over a dozen virtual instruments that can make measurements like general bench instrumentation equipment. So we're here at IMS 2023 in San Diego introducing a new virtual instrument called the Vector Channel Analyzer, or VCA. This is our VCA instrument here. It measures S-parameter S21 measurements, which is forward complex gain or transfer function, and displays it in the standard format of gain, phase, and group delay. So we'd like to demo the VCA for you today. We're going to measure a typical RF filter. It's a bandpass filter. First, we have a calibration that we'll do that I'll show you very quickly. But first, let me point out some key points of the VCA itself. It displays the transfer function measurements in the standard gain, phase, and group delay format. We've got user controls for setting the configuration of the measurement. That's just an RF frequency, a span, and a resolution. The box the 3100 can measure at RF frequencies up to 6 gigahertz, and the VCA has an instantaneous bandwidth of about 50 megahertz max. So we've pre-configured that, and we're going to go through a calibration stage to remove the effects of the platform itself before we introduce the filter. To do the calibration, we've introduced a short load, a through load, between the two RF ports, the transmitter and receive ports on the 3100. And then we've taken a measurement under our calibration tab here. We've taken a measurement, and you can see that there is some out of flatness in the magnitude. The phase and the group delay have little information, and they're flat, but we'd like to correct for that. So we'll apply the calibration, and now we've got zeroed out traces. So we're ready to introduce the device under test, which will be our filter. The filter we're going to test is a bandpass filter for the 900 megahertz ISM band. It's about 20 megahertz wide and has about 40 dB of sideband suppression. So when I plug that in, we'll be able to see that response on the traces. So let me get back to the VCA tab. So we completed the calibration, and we've inserted our bandpass filter DUT. So now we're measuring the response, the transfer function of the DUT. It's set at a 900 megahertz, about 900 megahertz center frequency. The span is about 50 megahertz. That's the maximum for the VCA. You can see the magnitude trace. The pass band is about 20 megahertz wide. You can see that in the trace. The skirts are down about 35 to 40 dB. So that's as expected. In the phase response, you can see in the central portion there's a nice linear portion of phase, but there's significant curvature at the ends. Now that shows up as group delay on the edges. That group delay from max to min is about 100 microseconds, so that's a significant amount of group delay. But of course that limits you to just the 20 megahertz of the central band. So that demonstrates, I think, the utility of the instrument. We've got some user controls that allow better viewing of the different plots. For instance, we can turn off one or both of the phase or group delay displays to give us better resolution in viewing, if we like that. And we can also set different resolutions for the magnitude trace. It takes about 2 updates, about 2 seconds to actually show up. So we can zoom in and look at responses. We've actually got a significant little dip there that is definitely of interest to system designers. So we can go back to a default. We've got an automatic smoothing filter on the group delay. The group delay is a derivative of the phase response, and it's typically noisy since it is a derivative. Let's see, in the phase response, we can apply this aperture without any filtering at all. Let me demonstrate. This is just a standard boxcar smoothing filter. When it's only a single unit long, it's quite noisy. So that's the actual trace. It's the derivative of the phase. But applying some depth to the averaging filter, we get a nice smooth trace, and we sacrifice a little bit of the peaking, the peak excursion of the trace, but we can certainly see a smoother trace, and it's easier to just absorb mentally. We also have a feature that does automatic phase ramp correction. There's no connected reference between the transmitter and the receiver. Now that's got a big advantage in that the transmitter and the receiver, if on two platforms, can be physically separated and connected by an over-the-air link. But when they're on the same platform, they could be connected, but we don't do that because we have a way of removing the fractional delay effect that gives us a ramp in the phase. So without that, if we disable that, you can see from measurement to measurement, that ramp will phase up and down, and you can see the displacement of the group delay when it does that. But when we enable it, it stabilizes it, and we can see a stable measurement. So those are the key features of the VCA. We've measured a bandpass filter for the 900 megahertz ISM band, and we see the gain response and the frequency and phase response as expected. So this is a new virtual instrument on our ATS 3100 radio test set. Again, it's got 6 gigahertz RF frequency range and about 80 megahertz of instantaneous bandwidth. And we've got a whole suite of other instruments that are on board. So we're adding the VCA to this suite of generators and receivers and demodulators and spectrum analyzers, as well as audio frequency instruments as well. So thank you for your time. Appreciate you listening. Have a good day.